All right, so let's get it started. So last time we started talking about cables, and I said the special thing about cables is that you can only expect normal forces in the cables, and I said before that we try to make our structural members have less bending moments because bending moments cost us a lot of money. So as you all know, do you guys remember our mission as a structural engineers? That we have first, if we have a structure, I'm gonna add to our mission a little bit. If we have a structure, we have to calculate the loads. By the way, the calculations of the loads, sometimes it's not that easy. Because you guys know, like, loads calculation include that you have to account for dead loads, you have to account for live loads, you have to account for seismic loads, wind loads, maybe, I don't know, if you are designing a military something, so you have to account for explosive loads. So there's a code, like, I'm not sure if you guys are familiar with the ASCE 722, I guess, the one that is out there.
22.
So this code is just have how you account for loads. Doesn't have anything about design of a structural member. A big code. Maybe I will bring it one time when we get into the seismic load modeling. That code is like, I don't know, hundreds of pages. It tells you how to account for the loads of the structural member. There's a chapter for dead loads, chapters for live loads, chapter for rain, snow, seismic, wind. By the way, as a structural engineers here in the US, you have to look in this code and you have to be familiar with this code, because designing any structures like this one, you have to account for the live load in this structure. You have to account for the dead load, the seismic load. Without load background, how you are going to design structures? So loads is very important. So that's one thing as a structural engineer, we have to be familiar with the load modeling on our structure system. So this is a basic step. So if I were you and about to graduate and work in the industry, I have to have a version of this code, look into it and see how the codes are modeling these loads. All right, so once you know how to model the load, the thing is also you have to learn how to pick a structural system for your building. Like building like this, I believe this building is a steel structure. So maybe other buildings are concrete. When to pick steel, when to pick concrete, you have to learn that too. And if it's a steel or concrete, this is the material, not a structural system. We are talking about the material of the system. Some materials are wood, so there's a lot of materials out there that we can pick from. So you have to know where to pick the material, like wood, concrete, steel. And if you pick the material, what system that I'm gonna build? We talked before about the simple beam system. There's other system like continuous systems, like you will have something like this. That's a continuous beam system. You can have frames, something like that. That's a structural system for our structure, and this is based on the span. So there's some special structure that requires a special system, so you have to know when you are going to use the system. Like the slab systems has different types. I'm not sure if you guys heard about solid slab. Have you heard about that term? Solid slab system is a slab that is that has beams and columns. Like if you guys remember before when we talked about the loads, how they get transferred. Solid slab system when you have beams. If you don't have beams, the system is called flat slab system. So the load transfer, the difference between the load transfer system between these two systems, in solid slab system, this is the slab, and then you have beams here, and then there's columns here, okay? So if the load goes from the slab system and throw the loads to the beam system, and then the beams throw the load on the column system, that's a solid slab system. But if there's no beams, and it's only slab, and by the way, it has a special design. So it's only the slab, and the slabs throw the load right away to the columns, so that's a flat slab system. So there's a solid slab and there's a flat slab system. There's other slab systems we talk about, like last time there's a system is called ribbed slab or a waffle slab. Have you guys heard about the waffle slab? The waffle slab is like, it's rather than have a thick slab that is 30 centimeter, because the thing is, the more the span, like if this span becomes more wide, the thickness of the slab need to be much bigger. The more it's gonna be much, because you need more stiffness. So that's what. So sometimes, but the thing is, you don't need all this thickness. This thickness is coming, as I said, from the bending moment. Like, because the thing is, look at this thing. This is L, right? And the moment that happens here, we agreed that is WL squared over 8. So the more the L, it is getting square the bending moment. So the bending moment is getting much more. But this bending moment is in the middle. That's the maximum moment. So what happened on the side? It's getting less. That's a one thing. And the thing is, this bending moment make tension compression. Like the bending moment want to make the slab like this. So the thing is, you need tension down, you need something to resist the tension down, and something to resist the compression up there. So what we do in the ribbed slab, it's rather than having a very thick, maybe let's say 0.4 meter cross section of a slab, like let's assume this is the slab, and I have a column here supporting this slab. So same slab is something like this, and I have my column like that, and I'm gonna do something. I'm gonna only make a slab thickness up there, that thing, and put some ribs here and make this part empty, and then a rib here and make this part empty. Same thing. Oh, let's say this is solid. So what is going to happen here? The thing is, as we said before, bending moments are very sneaky loads. They have tension and they have compression. And so where's the tension and where compression depends on the nature of the bending moment. Like if you are in the middle, like let's say this beam, middle is have a positive bending moment. So we are talking about compression at the top, tension at the bottom. But here, look at the bending moment here. It is something like this, and it goes negative, and it goes positive, and it goes negative, and it goes positive, and something like that. So the bending moment is different here. Like if you have a column here, so it's gonna be something like this. But if you have a span, it's gonna be something like this. So the tension and compression keep getting changed. So we have to take care of that. So that's why we say that the bending moment is very sneaky. It keeps changing over, like it depends on the location. So bending moments is like, it's hard to deal with. But the waffle slab system or the ribbed slab system deal with that way. Say, okay, I have compression up, so I'm gonna put slab thickness up there, and I'm gonna make some ribs and put some steel here. And then this, I'm not gonna put concrete here. I'm gonna put a material that is more cheaper. I'm gonna put foam, I'm gonna put something else. Or I'm gonna leave it empty and use it for architectural shape, all right? So this is called ribbed slab system. And they both have the same thickness. So I saved in the concrete. So that's also a different system. Sometimes this ribbed slab, sometimes it's one way, sometimes it's two way. Two way, that means I only have ribbed that way. Sometimes you are gonna have ribbed two ways. It depends on the system. You can use both, all right? So there's a lot of systems out there, but it depends on your span, which system is gonna be more economical for your span. So like let's say I'm gonna use a solid slab system. We usually, solid slab systems is very economical in between 4 to 5 meter span. Once it exceeds 5 meter span and becomes 6, 7, it's not gonna be economical. It's gonna be very thick, and you have to have a really deep beams. So, and then we go to the next option, the flat slab system. So let's put it here. This is a flat slab system. And this is waffle slab. And so once you have a column is bunching right away in the slab, that's called a flat slab system. But if this column has something like, let's say you have a beam like this, and you have a column supporting this beam, and your slab is something like this, so that's your slab system. Let's say and you have a column like this, That's called solid slab system. So basically the load goes from the slab to the beam and from the beam to the columns. So that's solid slab. We learned F3 system. By the way, this is the basic SWE system in a structural engineering. So designing any building, it's either a solid slab, a flat slab, sometimes it's waffle slab. So, but typically, most of our system in any building, it's a solid slab or flat slab. Do you have beams or not having beams? And our main issue with the flat slab system is the bunching. Like the columns, sometimes there's a typical failure in the flat slab system. Since there is no transition between, or a smooth transition in the load between the slab, the flat slab system and the column, sometimes the load, when it gets too much, the flat slab leave the column and the column bunch the slab. Like assume that this is your slab and you have your column like this. If you didn't design for bunching around this column, this area might have some failure. So one of the checks that we do in the flat slab is the bunching check. If this is slab, however, in the solid slab we don't do this check. Why? Because the slab, it doesn't throw the load right away to the column. There is a beam that is very stiff that take this load. Bunching is like the thing is, okay, let's say that you put load and this is slab, a very heavy load. Cracks is gonna start showing up here and showing up here, and then this whole block is gonna leave the concrete. So that is the bunching, like the column is bunching the slab.
Like if you have a piece of paper and you put a pen.
Yeah, exactly. And actually this is a problem when we model on SAP 2000, and we're gonna come to this problem. When we model columns in 2D, what we do, we put hinge, right? But the hinge is only provide support at a point, right? Just one single point. But in real life, this is not a point. This is a column that has a cross section. So when we do this on SAP 2000 and model this, we will find that the bending moment, the stress is at this point very, very high. But this is not realistic. Why? Because the model modeled the intersection between the column and the slab as a bend, a very point. So actually the model feels that the slab system is supported on a needle, as you said. So it makes a lot of stresses here. So that's why we try not to calculate the bending moment at the center of the bend. We try to imagine that there is a column with the dimension of the column at this bend and take the moment at this part, okay? All right, so this is a bunch of the systems out there. And by the way, these systems are just to like find a way to resist the bending moment, okay? All right. And by the way, sometimes the client doesn't like the waffle slab system, but we will tell him, hey, your span is like 15 meters. And if we use flat slab system, it's gonna be very expensive. He's like, I don't care. One of the projects that I work on before I graduate, the slab thickness, there was a story, and I believe it was like the openest space between the columns around like 15 meter and 15 meter, huge. So what they did, they make a slab thickness around 45 centimeter, like 1.5 feet. And not only this, the thing is the bunching was very high, so we make something that's called drop panels around this column. Like at the column section, we increase the thickness of the slab because of the bunching. That's a heavy concrete, a lot of concrete. So, and definitely a lot of reinforcement at this area. So we use sometimes a flat slab with a drop panel. This is called the drop panel. And sometimes we put something like this as well. So, because we want to resist the bending moment and the bunching. There is a lot of stuff that keep getting developed. Yeah, you have a question?
We use monolithic beams.
We use what?
Monolithic beams.
What do you mean by that? You mean, monolithic is mean that they are poured together.
Yeah.
But that's actually all of these. The columns and the beams are both bored inside. Monolithic means that they are bored inside, not precast. So precast is like you have this column board in a workshop or something, and the beams and the thing, and you come on site and you just like put them together like Legos. And when you come to the site, some sites like they come at this joint and they just board this joint in the site. Okay. All right. So this is some of the systems. There is other systems. As I said, there is something called paneled beam. Paneled beam is for huge spaces that even maybe can exceed 20 meter and 30 meters. Like you have a really deep beam, like 1.5 meters. They are all like closely spaced. By the way, the spacing between these strips is very small. Like we are talking about maybe less than 0.5 meter. Okay, same thing with the paneled beam. You can make this paneled beam is a very close concept to the waffle slab. Same thing, but this strips is very small. We are talking about.
There's no, like they're that close?
The spacing
Yeah.
between the ribs.
Yeah.
Yeah, the ribs is like very small. We are talking about like this,
Oh,
very small. So you will feel that the whole ceiling is like a waffle because it's very small. That's why
But
it's
there
called
are-
waffle slab.
There are larger.
There is larger. This is called paneled beam. When the spacing like gets to be 1 meter or something, that's a paneled beams, and the
Okay,
beams
okay.
like gets
Okay.
really thick.
Okay.
So that's some of the systems. However, these systems can work for like we said like right now the range is around what? Around 20, 25 meters. Maybe you can go to panel beams, but the thing is, what if the system is like 30 meter or 40 meter? These systems is not gonna work. It's not gonna be economical at all. The bending moment is gonna be huge, and you need to find a way to deal with it. That's why we come to the concept of arches and cables. Okay, let's switch the camera. So cables, most of the applications, you will really find cables application in residential buildings. Mostly the cables are like in transmission lines, cable stayed bridges, suspended bridges. So that's where most of the structure where we use cables. But arches is the same thing. Like, but the thing is, arches we can use them in other applications. Like sometimes you can find like sometimes we use them for architectural design because they have a really good shape. All right. So arches has a little bit more application. We use them in bridges too. Sometimes you make like a bridge and you make an arch on top of it, and you make some wires to catch the bridge from it, like something like this. All right, let's say that we have a huge or a long bridge. We are talking about like, let's say 300 meter span, like from here to here. If you made anything here, it's gonna fall. That's like a huge beam with a lot of bending moments. So what you do is like you make like a huge arch, something like this, and then you throw some cables to catch this bridge somehow. So look at the system. How is the loads are transferred? The loads start from here. Like let's say you have your car here. By the way, as a structure engineer, when you go anywhere on a bridge, on a structure, like even me right now, when I go in any space, I look at the system. What kind of system is that? How is the loads getting transferred? Like I go to Walmart, so I have the corrugated sheets and then give the loads to the there's a small truss systems and then give it to the girders, and the girders so I load at the load transfer from the loads until it comes to the columns. Where's the columns and where's the beams and where's the girders? That's what I do. Same thing with bridges. Look at this bridge. Let's see. How about you guys tell me? Like we have cars here, okay, and pedestrians and whatever. How is the loads are getting transferred from this until it comes to the foundation? Because I told you our mission is try to track the loads from the load to the foundation. We need to transfer the load of this car here. How this is gonna happen? Can we track it? Okay.
Some are going there.
It's gonna go to where?
Some to the cable, some to the
No, before the cable.
slab.
To the slab system of the bridge. And then the cables, so the
Or the
cables is
column.
gonna take, like this bridge want to go down, but this is gonna take it like this. That's how we represent the tension in the cables. And you will tell me why I put this in this direction, this is compression. No, this is how this arrow's coming outside of the point, that means there's a tension on it, okay? All right, so from the cable, and then the cable takes it where? To the arch system, and the arch system transfer it here, and to the columns, and then it comes to the foundation. All right, so that's how we track the load.
Does part of the load from the slab go directly to the columns?
Maybe this part. This part is gonna take it. Okay, each one of these cables take the load from here to here. That's how
Only
we
the
do
cable
load.
takes it.
Kind of. The thing is, you have to take this slab system by itself and then put it as a support system, because these cables make a support system. You can make it down or you can make it up, and then you solve this for the reaction.
Okay.
And this reaction is gonna be transferred to the cables. All right. So this arch, okay. So right now I transferred the load from the slab system to the cables and the cables to the arch. The thing is, this arch is a little bit tricky. What is the curve of the arch? Why did you make the arch like this? Why you didn't make it like that? Why you didn't make it like that? How can I make an arch that's economical? For an arch to be economical, it should have the least amount of bending moments. We need to induce bending moment in this arch minimum. That is the economical arch that you should have. The good thing about the cable system, it's never gonna have a bending moment, but the arch, it might have a bending moment. Okay, remember this. Cables will never have bending moment. Do you know why?
Cannot resist it.
Because they cannot.
What was the answer?
Cannot resist.
They cannot resist it. Excellent. And why is that?
Because they cannot compress.
Exactly, like let's say this is the cable. Whatever you put in this cable will never take any bending moment because it cannot resist bending moment. It doesn't have the stiffness enough to resist bending moment. But the arch system is concrete. It can't resist the bending moment, so it can take it. But our job as a structural engineer, I want to minimize the amount of bending moment that the arch can absorb it. But this one would never take it. So let's say that you have something like this and you put one load in the middle, it's gonna make like this. It's gonna make a shape that make the bending moment 0. If you put two loads, it's gonna shape in a different way. Like this, it's gonna make it this shape. If you put it in the middle, so the shape of the arch is, the shape of the cable is gonna make a shape that is gonna make the induced bending moments 0. All right? So like try to put your fingers anywhere here. So basically it's gonna make different shape that can make the total bending moment on this cable equal to 0. So for an arch, it's not gonna do that way. The arch is gonna be having one shape. You put one load, it's gonna have the same shape. Another two loads, it's gonna have the same shape. So depending on the load and geometry, you are gonna have completely different internal forces. But as a structural engineers, if we wanna make this arch have the least amount of bending moments, we need to find a way to do that. And to find a way to do that, we are gonna be inspired by the cable. So the cable, the shape of the cable, or the shape that the cable take after you put the load, is called funicular shape. Okay? Remember that. The shape that the cable is taking after you put the load, it's called a funicular shape. If we were able to come with an arch that is gonna make a funicular shape, you are gonna guarantee that the bending moment is gonna be 0.
Spell it out.
What?
Funicular.
Oh, okay. Funicular. Okay. All right, so let's put it here. All right, so let's say our cable is something that is our cable. So the thing is, if you put one load, it's gonna make something like this, right? It takes this shape. Why? Because with this load and this geometry, the bending moment is gonna be 0. But if you put two loads, or if you put another load here, it's gonna take that shape, right? So it keeps changing the shape so that it can make the bending moment equal to 0. The thing is, when you put the load, the cable didn't resist it. So it make a deformation that makes the shape has a bending moment equal to 0. So the arch is the same thing. If you want to have an arch, like let's say,
So if something is deforming, it doesn't have a bending moment. If it's deforming a lot, it doesn't have.
because the thing is,
a
it
low
doesn't
bending
have the
moment.
resistance to make a bending moment. So that's why it releases the energy into the formation
Got it.
and deform in a way that make the bending moment equal to 0. But the thing is, the arch cannot deform. You have to know the amount of loads that you have so that you can shape the arch in a way that can make the bending moments equal to 0. So The thing is, with the same system of loads that you have here, you have to flip this like this, like imagine that I flip it and I put the same loads. So basically, the arch, the funicular arch, is a flipped cable for the same arch that has the same geometry and same loads. So basically flip that way and make an arch, that's a funicular. And for a funicular shape to be funicular, it has to satisfy the general cable theory. Do you remember, guys, the general cable theory? That the H, the horizontal load, multiplied by the sag is gonna be equal to the moment at the section. So let's say this is the chord and this is H. All right? So the horizontal force that we have here multiplied by the H is equal to the bending moment at this cross section. So for this arch to be funicular, by the way, why is that? If you guys remember how we drive this last time, we drive this last time because the cable cannot take bending moment at any cross section. So basically this rule says that the bending moment at any cross section here is equal to 0. That's the rule that is going to set. If your arch doesn't satisfy the general cable theory formula, so there is definitely a moment. Like if H multiplied by H doesn't equal to the MZ, like here, if you take a section here, and you try to take a section in this arch, and you take the moment in this arch, this moment is MZ, is not to equal to H multiplied by the H here, so that means this arch has a bending moment. Does that mean that the arch is bad? No, the arch is not bad. It didn't have 0 moment, but definitely the moment is way less if you use the simple beam, okay? Sometimes there is no way that you can make 0 bending moment. Usually the arches, the best arches has at least 1/10 of the amount of bending moment that develop at the simple beam. Like let's say, if you use a simple beam here, and you put a bending moment, this bending moment is gonna be WL squared, so if it's have a distributed load, it's gonna be equal WL squared over 8. So it's gonna be like you did a great job if you make this bending moment equal this, like, let's say, WL squared over 8. To make the bending moment here at the maximum section, 0.1 WL squared over 8. That's really good if you can get that. But theoretically, we can reach 0 bending moment if we make the arch funicular, all right? If it satisfies this formula. So actually, let's solve a problem and see how. So in the test or in a quiz, I'm gonna ask you a direct question. Actually, it's one question. I'm gonna give you, for example, Alright, so that's an arch. Imagine that this arch is like the arch that we made for this bridge. Do you guys remember when I said that this takes full load and this takes half load? So when you take a full load, it's gonna give you 60 kilo-pound. But if you take half load on the columns, it's gonna give you 30 kilo-pound. Alright, I'm gonna ask you one question. This height, I give it to you. This height is 36 foot. I didn't give you this height. Or this height, H1, I don't know that. All what I know, I want an arch that has a maximum height of 36 foot and to cover a span of 180 foot. That's around 60 meter space. All right, and I ask you one question. This question is, establish the funicular shape of the arch.
Establish it.
What does that mean? Establish the funicular shape of the arch, like tell me what is the geometry of the arch. Mean find H1 and H2, because I want to go in the site and build this bridge, so I want dimension. So basically find H1 and H2. Once I said funicular, first thing that should come to your head, the general cable theory. This theory. H multiplied by H is equal to the moment mz. Alright? So, and by the way, if you guys remember the general cable theory, what does that mean? That you have to draw the equivalent beam of the arch or the cable and try to find the bending moment on this beam. Do you guys remember that? We did this in the cable last time. We had a cable and we said that the arch or the cable side, H multiplied by H, you get it from the cable, and the moment you get it from the simple beam equivalent to this beam. So the first thing I do once you hear general cable theory, this, or once you use general cable theory, you draw the equivalent simple beam of this system. And then you put the same load. I'm gonna put 60, and another 60, another 60, and I have 30 here. Same thing here. 30. That's how general cable theory is. You get the equivalent simple beam of the cable or the arch, and then draw the bending moment on this system. But to draw the bending moment, I have to find the reactions. Can you guys tell me the reaction of this system? It's a symmetric, right? So I can sum all these loads, 60, 120, 180, 240, 300, 360. So I have reaction 180 here and 180 here. Okay? So this is a concentrated load. So basically you will come at each point and try to find the bending moment. So find the bending moment here is going to be 180 minus 30, 150 multiplied by this distance, which is 30 foot, and then you will find the bending moment at this point. You will do the same thing to find the bending moment at this point and the bending moment at this point. And then you draw a line between all of them, and here is going to be all of this is a positive moment, so the values is going to be 80, 100, 70, 200, 45, 100. That's the bending moment on the equivalent sympathy. Alright, so by the way, we found the reaction here 180, but we didn't find the horizontal reaction. There's multiple ways that you can find the horizontal reaction. By the way, I can use this, and actually, if you don't want to use the general cable theory to find the horizontal reaction, you can use the basics of structure analysis. This is an intermediate hinge. Try to take the moment from the left side, and you can find the horizontal reaction here. Can you tell me, is the horizontal reaction that way or in the opposite way? Which one? 1 or 2?
The horizontal reaction.
1.
Yeah, should I pick 1 or 2?
1.
Why? Because this arch has the load 1 moment, so this is providing reaction the other way. If it's cable, it's the opposite. This one, when I go down, so this is gonna go the other way. Alright, so I want to find the horizontal. Basically, you can apply the general cable theory or structure analysis. If you take the moment all the left, it's going to give you the same thing. But I can apply the general cable theory, H multiplied by H, add H3 is going to be equal the moment at point 3. So H, I don't know it, but I know the height at 3 is equal to 36 foot. And I know the bending moment at 3 is 8100. This is going to give me a horizontal force equal to 225 kips. All right, I found it. Does anybody have any problem with that? Try to find the bending moment at this point from the left side. It's going to give you the same answer. All right, so the second part, I want to find the height at 1, this point. I want to find this height. So I'm going to say 4h1. How can we find it? Same thing. I'm going to multiply h, multiplied by h1 is going to be equal the moment at point 1. H, I already found it, 225. H1, I don't know it. The moment at 1 is 4500. This is going to give me H1 of 20 foot. Same thing, I'm going to do it 4.2, 4H2. I'm going to say H multiplied by H2 is going to be equal to the moment at 2. So this is going to give me 225 multiplied by H2. M2 is equal to 7200. So H2 is going to be equal to 32 foot. And you have to use your sense a little bit. Let's say you got H2 equal to 50 foot.
No way.
Would that make sense? You have already, this one is 36, so definitely these are way less. Well, actually, general cable theory helped it a lot in finishing this problem very fast. So, once you said that this point satisfies the general cable theory, so that means this bending moment is 0. Alright? Okay. And why is that? The thing is, you said here that the bending moment that comes from all the loads from the left side, like 60, 30, whatever the load that you have, is equivalent to the moment that comes from the H multiplied by H2. That means you balance it the left side and you make it 0, so the right side is 0. So basically this point is like an intermediate hinge. And this point is going to be like intermediate hinge. So you make all the cross sections has a 0 bending moment. Alright, so this is if it's concentrated load. So what if it has distributed loads? What is going to be the case? So let's have a distributed load problem.
The only thing is that we found these values for H and for N based on the shape and the values that you gave, like the problem had.
Well, the thing is, this is 36 that I gave it to you. This one you can make it a little bit up and down. And this one you can make it a little bit up and down. So the more that you make it up and down, it's going to adjust
Okay,
the bending
so
moment.
it's 0 at that height. If it was 21
Yeah,
feet.
like if you made it like this,
Okay,
it's gonna be different.
okay,
If you make
okay,
it like
okay.
this, it's gonna be different.
Okay. But of course, if you change the height of the middle one, the other is also.
Absolutely,
So the
it's gonna
middle
be
one is
different.
what governs.
Yeah,
The
because it's gonna
moment
change the whole geometry.
Okay.
Okay, so let's do a distributed load one.
Hey, Professor, quick question.
Yeah.
The only reason H is the same on both sides is because the loads are like symmetrical on both
Oh
sides?
yeah, because I have a symmetrical arch, so I didn't care about making this side, so that's why I did the one side.
Okay, thank you.
Sure. Okay, so let's say we have distributed loads. Same arch. Has W.
Is that a roller or a fixed?
This is hinged, not fixed. There's
Like pin.
intermediate, yeah, pin. So I'm gonna make this arch in a general symbols, like I'm gonna say that this is L over 2 and this is L over 2, this is W. Yeah, and then let's say for arcs support distributed load. Okay, so let's say we have this arch. By the way, if you want the equation of the arch, same thing like we did last time for the cable, you can assume that you have x-axis that way, and you can have y-axis that way, or you can make it up. And then you can say this point at, this is y, and you can say that this arch has an equation is equal to a multiplied by x squared, and you say at y equal to h, this height is all h, a is going to be multiplied by x is going to be equal to L over 2, right? This point is in this arch, like it's something like this x, y, and you have something like this. At this point, this height is h, and this is equal to L over 2. So I know one point on this arch, the x and y is equal to h, x is equal to L over 2. So basically you can get a, do you remember the mistake that we did last time? We did L squared over 4. So the thing is, this is gonna be equal to 4h over L squared, right? Or did I make it? Right, so this is gonna be L squared over 4 multiplied by h, and then you divide by L squared, is gonna give you something like this. So the equation of the arch is gonna be equal to 4h over L squared multiplied by x squared. That is the equation of the arch. To be funicular, it needs to be this parabolic. So let's find out, is that true or not? To be true, I have to take the moment at any cross section and give me 0. But to do this, I have to find the reaction first. As we said, we have to find the reaction before we do anything in the problem. So can you guys tell me what are the reactions here without doing any calculation?
W over 2. Well, W times L over 2.
W L over 2, right? Because
Over
this
4.
is whole W distributed over the length L, so the total load is WL
Over
and over 2 supports, so this is going to be WL over 2 and WL over 2. So 2 loads divided onto reactions. How about we get to the horizontal load? How can I get it? I can do the same way. I can take the bending moment at this support from the left or the right. So I can say, let's say that this is point A. I think this point, this is, I named this B and I named this C, just to be consistent with. Okay, so I'm gonna take the moment of C and I'm gonna say that this is positive, equal to 0. I'm gonna take it from the left. All right, can we take the moment around C from the left? What is gonna show up? Is WL over 2 is gonna be positive or negative? Positive. So I'm gonna have WL over 2 multiplied by L over 2. How about H?
H.
It's gonna be positive or negative? Negative H multiplied by H. Do I have any other loads that make bending moment around this joint?
No.
We have this load, distributed load. That's why maybe it's away from the arch, but the thing is I can't put it on the arch. I can, but it's gonna make the arch look ugly. Like,
Wouldn't that be in the middle?
I can make it like this, and I can say that this load is W, and it's ton per meter, and I can say it's a horizontal projection. So, but the thing is, we put it that way. By the way, when you have a textbook, they represent. What is your question?
No.
Okay.
It's okay.
When we have a textbook, you will find they represent the load differently. So sometimes you will find, like, let's say this beam, and this beam. Sometimes they will find that the load is something like this, and they make it like that. And sometimes they will make it something like this. And sometimes you will find that the load is gonna be something like this. And let's say I said this is 2 ton per meter, and I said this is 2 ton per meter HP, and I said this 2 ton per meter, and this is 2 ton per meter. By the way, all of them are different.
HP, what does that mean?
HP means horizontal projection. So 2 ton per meter, that means this 2 ton per meter is distributed over the inclined length of the member. Like let's say that this is L, so the total load is going down, and it's 2 multiplied by L. Okay? But if I said 2 distributed over the horizontal projection, that means this 2 is distributed only on this part. So the resultant is going to be 2 multiplied by L cosine theta, only at the horizontal projection part. This one, I don't have to write it's a horizontal projection. Let's say that L cosine theta is L dash, so this is 2 multiplied by L dash. So L dash. So the resultant is going to be equal to multiplied by L dash, the horizontal projection of the beam. This is going that way, because the direction of the dash is going that way, and 2 multiplied by L. So you should have known this from the basic structure analysis, because that's how we represent the loads on the beams. I'm just giving you this, not a problem. This is how you read the problem. If you open a textbook and you saw how is the loads are drawn, so that's what does it mean. If I see 2, that means it's distributed on the whole length. 2 HP, that means it's distributed on the horizontal length. So this is the same like this. All right?
So that one's a horizontal projection.
That one, since I put it that way, that means it's distributed on the horizontal projection. However, in real life, mostly this load is the own weight of the arch. The own weight of the arch is not horizontal projection. It is on all this curved length. So what we do, we calculate the load of the whole arch, and let's say the load of the arch is 50. And divide the 50 over the length L. Let's say that the L is another 50 meter. So that means the 50 over 50, so it's 1 ton per meter. Okay? All right. Anyway, so let's get back to this. So this load is a horizontal projection, and I have half of this load. Let's get back. We were taking the bending moment around this thing. So can you guys tell me how much load I have here making bending moment? And is it positive or negative? I know we talked a lot here, and we are getting back to the problem. But remember, we were taking the moment about C left, and this load was making WL multiplied by L2, moment positive. H is making moment negative. W is making moment positive or negative? Negative. Negative what? W L over 2 multiplied by L over 4. It's going to be equal to 0. Because this load, the total resultant of this load is W multiplied by L over 2. That's a resultant. But the arm of this is L over 4, this distance. You guys get it?
Yes.
Alright, so once you solve this to find the horizontal, actually, I have H, usually from the geometry, I have W, I have L, I have all this except this. That's what I don't have. So once you solve this and put everything together, you are going to find that this is equal to WL squared over 8H. Alright? Okay, so here. Right, so I found H right now. The next step, I want to find the moment at any point at the arch. Let's say I'm going to pick this point at any section. M, the moment at any section. I'm going to find what is the value of this moment in terms of symbols. Okay? And then I'm going to make this moment is equal to 0. And try to get the function. Once you make it, so this is the function that makes this arch funicular. So let's find what is the value of the bending moment at this point. Like let's say this is point D, and this point D is at a distance.
H minus y.
Let's say this is the distance, and this is the distance is equal to x, and this distance is equal to y. All right? And I want to find the moment at D. The best moment to get the moment at D, I'm going to get it from the right side because it's less stuff. So I'm going to say find the moment at D, any point. Moment at D is gonna be equal to, and I'm gonna say, let's say that the positive is going, let me make it the same like here. Okay, the positive is gonna be something, that way is the positive, all right? So let's find, what is the moments on D from the left side? I have WL over 2 multiplied by this distance. This distance, do you guys know what is this distance? From the geometry, you have, this is L2 and this is X. It's gonna be L over 2 minus X. Okay, that's for L2. How about H? It's gonna make a negative moment multiplied by, what is the arm of H? The horizontal force. It's gonna be the total H minus Y, this whole H minus this distance. And I have the distributed load on this part. This distributed load. So this distributed load is gonna make a negative moment, and this W multiplied by this distance, which is gonna be L over 2 minus X, and this is gonna be L over 2 minus X over 2. That is the bending moment around this section. Once you open this and substitute, we got H over there equal to substitute this here, you will find out that the moment at this cross section MD is going to be equal to W L squared over 8H multiplied by Y minus W X squared over 2. That is the general formula of the moment, all right? Okay, that is the moment at any cross section. If you want to find the moment at any point, try to substitute with X and Y. Here, let's say that the X, by the way, this is our coordinate. I want to find X and Y, I substitute by X and Y, I'm going to find the moment.
Do you have to consider negative in that case if you go to the left?
Yeah, if you go to this way, it's going to be negative. But Y is positive because I assume that Y is positive that way. But that way is positive, that way is negative. So the thing is, for this arch to be funicular, the moment at any cross section should be equal to what? 0. So for, switch the camera, for arch to be funicular, MD at any cross section should be equal to 0. So let's put this rule is equal to 0. 0 is going to be equal to WL squared over 8H multiplied by Y minus WX squared over 2. Once you solve this, get the W over the W and 2 and make this 4, you will find that Y is going to be equal to (4H over L squared multiplied by X squared. That is the equation of the arch, the parabolic arch, that is going to make this arch funicular. Funicular means that the bending moment is going to be equal to 0. Look at this equation and the equation that we got at first. Same one. Y equal 4H over L squared multiplied by X squared. Okay? So it leads to the same thing. Alright, so this is for Y. So let's find out what is the compression in the arch at any cross section. So I said some notes here. I'm going to tell you what did I write here and what does it mean. I said this is parabolic equation, this equation. Even if parabolic arch is fixed. This is hinged. If a parabolic arch is fixed with a uniformly distributed load, would it still produce direct stresses? Direct stresses mean normal stresses, that mean normal forces, there is no moment, at all sections, assuming that there is no significant change in geometry from the axial shortening. That means that if this is the same geometry and this is fixed, it's still is going to be funicular. All right, let's get the total axial compression. Right now I have the equation of the arch, but what if I want to find the compression of the arch? Do you guys remember this rule? T is equal to H over cosine theta. This is the tension in the cable at any cross section, depending on the theta. All right. So, but right now, this is going to be shifted to be compression is going to be equal to H over cosine theta. Same thing in the arch system. Okay, I know the horizontal force. We already got that the horizontal force is equal to WL squared over 8 multiplied by H. By the way, you can memorize this rule very easily. How? This arch has a distributed load, something like this. So if I made the equivalent beam is going to be something like this, and the moment is going to be WL squared over 8. So the moment, this is equal to the moment, and the height of the arch at this section is H. So if I apply the general equilibrium theory, the general cable theory, so H multiplied by H is going to be equal to WL squared over 8. So H is going to be equal WL squared over 8H. So that is the rule. So it's basically the bending moment in the middle divided by H. That is the horizontal force. So I know the horizontal force, but I don't know what is the value of theta. How can I get it? So if you guys remember, if I have the equation of the arch, what can I do to get the value of theta? So your arch has this equation. The function is fx or y is equal to 4h over L squared multiplied by x squared. That is the function. So if you want to know the slope at any point here, what should you do? You get the ddx of the function fx, which is y here, ddx of y. All right, so let's get dy dx. Can you guys differentiate this equation? It's going to be what? H over L squared multiplied by x. So that is the function of the equation. And this is equal to tan theta. So let's do a little bit of geometry, okay? If you know that tan theta is equal to 8h over L squared multiplied by x, all right? So let's draw a triangle. And this is theta. So if I said theta has an opposite over x, what is the value of this line?
Well, that would be
Like if I said that the height here is the opposite is equal to this value. To make tan theta equal to this value, what is the adjacent? It's 1, right? How about this? It's going to be Pythagorean theory, 1 squared plus this squared. So it's going to be 1 squared plus 8h over L squared x all squared. That is this line, right? Can we get cosine theta? Cosine theta is going to be equal to 1 over 1 plus 8h over L squared multiplied by x all squared. That is cosine theta. So basically, if you want to find t, you divide h by this value. So t, sorry, let's make it c because it's compression. You can use t, whatever you want. But I'm going to say, c is going to be equal to h over this. So it's going to be h over 1 over this. So basically, I can put 1 plus 8h over L squared multiplied by x all squared. So I got the compression in the arch. Does anybody have any problem with this equation?
yes.
Tell me.
Well, no, sorry, it's all good.
No problems?
No problem.
Okay. So what I did here, compression was the horizontal force over cosine theta, and the cosine theta is 1 over this. So this over 1 over the square root, so the square root is gonna come up to the top. All right, so we solved one with symbols. Actually, let's put this in numbers and see how it's gonna look like. So over there. All right, so my arch here is 70 foot and 70 foot, and I have a distributed load of 5 kilopound per foot, and the height of the arch H is equal to 42 foot. All right, and I'm asking you establish the funicular
Thank you.
shape. And this is ask number 1. Number 2, I'm asking you to determine the minimum cross section at x1, x2, and x3. Let's put the x's here. And I give you x1 is equal to 17.5 foot, x2 is equal to 35 foot, x3 is equal to 52.5 foot, and I give you the allowable stresses in the arch of the material, like let's say it's concrete, so this is the allowable stresses that should be generated here. Let's say allowable stresses or the capacity of the cross section. When I ask you about cross sections, by the way, when we do analysis, we don't want capacity because we don't do design. When we do design, you need to know the capacity of the material. What is the capacity of the concrete? What is the F yield of the steel? Once you hear FCU and F yield, that means we're going to do design. But in structural analysis, we don't have this, but let's do a little bit of application on designing the cross sections. Okay, so I give you an x coordinates, these coordinates, and I ask you to establish the funicular shape. Basically, I just solved this arch, and I found that the equation of this arch to be funicular is equal to, you guys, can you see, 4h over L squared multiplied by x squared, right? So if I want to find y1 is going to be equal to 4, h here is 42 foot, L squared, L is 70 or 140?
140.
140, because L over 2 is the 70. So we're going to have 140 squared multiplied by x, which is 17.5 squared. Y2 is going to be 4 multiplied by 4 square over 140 square multiplied by 35 square. Y3 is going to be equal the same thing. This is 42. Alright, so that's an easy one. I just calculate these numbers and you're going to find that y1 is going to be equal to 2.6 feet and 10.5 feet, and this one is going to be 32.6 feet. Alright, so that's for this one. And by the way, this is how we build the arches. Like when we go to the site and do arches, we make stations, and we know at each stations what is the x and y coordinate, and with total station, it's like a GPS thing or whatever technology that you're going to use, you keep locating these points. and then making them piece by piece. Once you make every piece, the more pieces that you have, the more the arch is gonna be more curved. If you make it rough, like if you take like just a few points, it's gonna look like a broken arch. All right? Okay, so we have Y1, Y2, Y3. We are done with number 1, establishing the funicular shape of the arch because we found the geometry. How about determine the minimum cross section at X1 and X2 and X3? To determine a cross section, you have to know what forces in this cross section. And we are talking about funicular arch. Do we have moment?
No.
We have shear?
Yes.
No, we don't. Because
No?
arch is going to be only having normal force. It's
There's
not going to
no
have
shear?
any shear.
Oh, but if you apply.
If there's moment, there's shear is going to be generated. Hmm? You have a question?
I was calculating the Y3 and I got 23.60.
Y3, is this 52.5 square?
Yes.
Let's see what they have. They have 32.6 here. 4 multiplied by 42 over 140 square. You think I got the same number? 23? Okay, maybe I change it
32
32.
instead of 30,
Yeah.
23.
Thank you. 23. Thank you so much. All right, so actually you can do it yourself. You can take a cross section and see if it has shear or not. Okay, so that's the one thing to do. But if moment got generated, shear is gonna show up. But since this is funicular, it's gonna only have normal
Can you
force.
have shear without moment?
Having shear without moment, I don't think so, because the thing is, shear is gonna be vertical force, and the vertical force is gonna make a moment,
Right.
because it's gonna shear
Right,
the section.
right.
So usually, we always name shear and moment are coupled forces. They always come together. But normal forces is uncoupled forces. It can be by itself. You can have tension or compression without shear and moment. But once you have shear, section is gonna have moment as well. So they are coupled forces. Okay, so we need to find what is the normal force in these cross section. To find this, we have this rule. Do you guys remember the compression rule? C is gonna be equal to H multiplied by this. So at each cross section, let's say I got H. Let's calculate H first. Do we have it here?
Yeah. H equals W squared over
Right.
8H.
H is equal to W L squared over 8H. So W is 5, L squared is 140, the square over 8 multiplied by 42. So H is going to be equal to 291.7 kips. Alright, I got H. So if you want to find the compression at section 1, and let's say the compression general rule is H square root 1 plus 8H multiplied by X over L the square all the square, right? So let's find the compression at section number 1. So it's going to be 291.7 square root 1 plus 8 multiplied by 42, and the X at this section is 17.5.
No, 2.6. At 1?
X1, not H1.
Oh, yeah, yeah. I
Okay.
was looking at Y.
So, and this L square is gonna be equal to 140 square, and all this is a square, right? Try to calculate this. The answer that I have here is 304.5 kips. You will get C2, you will do the same thing in the calculations here. All what is gonna change, so same thing here, same square root, same plus, same everything. The only thing that is changing is the X is 35. And C3 is gonna be the same number, same square root, plus, and the only number that is changing is the X, which is 52.5. And this one square. So you are gonna get these numbers 340.2 kips. And by the way, calculate C3 because I might mess up this number also in this calculation. So this is gonna be 392.4 kips. All right, so right now we know the compression. That's the end of structure analysis. As a structure analysis engineer, analysis, not a design. By the way, when you are a structure engineer, you do analysis and design, but this course is only analysis. Once you get the compression, the analysis is done. Once you give me internal forces, we are done with the structure analysis. If you want to shift to the design, you have to tell me what material you are going to use, what is the capacity of this material. Let's say we're going to use concrete, and the capacity of this concrete is 2,000 pounds per inch square. Okay, so if you want to find, that's very easy actually. Sigma stresses is equal to the forces over the cross-section area, right? So if you want to find the cross-section area, that's what design mean. Design, try to tell me what is the cross-section dimension. So the area is going to be equal to the forces over the stresses. So if you want to find the area of cross-section number 1, so it's going to be the force B1 over the stresses. So it's going to be 304.5 over 2,000. But pay attention, this 304 is kilopounds. So you have to multiply by 10 to the power 3 to convert it to pound, because this 2,000 is pound inch square. I didn't show it here that I multiplied by 10.3, but I did it in the calculation. So you find area number 1 is going to be 152.3 inches squared. You're going to do the same thing with the cross section number 2, 340 multiplied by 10 to the power 3 over the capacity of the section. So the cross section number 2 is going to be 171. Cross section number 3 is going to be equal to 392 over 2,000. So it's going to give you a cross section of 196.2 inch squared. So once you get the cross section area of each section, you are done with the design. So, but the thing is, let's add some excitement to this. We only have 2 minutes. Right now, you have A1 is going to be equal to 152 inches.
And 3 inches.
A2, 170. A3 is 196 inches squared, inches squared, inches squared. So the thing is, usually we make the width of the cross section is constant and we increase the depth. So if I assume that the B is constant for all these cross sections and B is equal to 10 inches, like let's say my cross section is something like this. I say that all the cross section has the same B, but they have different depth. So if you want to find the depths of cross section A1, you can divide A1 over 10. D2 is going to be A2 over 10. D3 is going to be A3 over 10. So basically this is going to be equal to 15.2 inch, and this is going to be 17 inch, and this is going to be 19.6 inch. So I got the dimension. So basically when you draw this arch in real life, it's going to be something, this is the cross section here. And the thing is, the cross section is getting bigger as soon as you come down, and it's gonna be something like this. Same thing from the other side. So the cross section here is like 15 inches. You go here, it's gonna be 17 inches, 19.6 inches, and it's getting bigger and bigger as soon as you come to the support. Where is the maximum compression? Why is that there's a maximum compression here? Because here is the maximum theta. You guys remember? Can you tell me what is the compression here? What is the value of the compression here? 0. No, there is a compression equal to the horizontal force. Look at this. So compression is equal H multiplied by this. So basically it's gonna be, all this is gonna be equal to 1.
Yes.
So H here, or actually you can say H over cosine theta. And theta is equal to 0, so cosine theta is equal to 1, so it's gonna be equal to H. The more that the theta is getting increased, the more the compression is getting increased. That's why the cross section is getting bigger. Look at any arch, the whole world. You'll find that the arch has the smallest cross section on the top and keep getting bigger as you go down. All right. So that's it for now, and we are done with the cables and arches. I will assign the homework today, and we are going to start a new topic next week.
Professor, I have a quick question. So for this,
From here to find the moment at any point. The moment you get to the right.
Yeah.
Right, only to the right. Why?
You can do it from the back. The thing is, the moment for the whole structure should be a proportion. But if you have an intermediate,
I can stop, Professor?
oh yeah, yes please.